You know, it's kind of wild when you stop and think about it. You're sitting in front of this box of electronics, but how does it actually work? How does it think? Well, today, we're going to pull back the curtain and find out.
I mean, think about it. You click a mouse, you tap a key, and boom, a whole universe just pops up on your screen. How in the world does that happen? Well, that's the journey we're going on today, from that one simple click to everything that follows.
So, first things first. Before a computer can build a universe or even open a file, it needs a language. It has to know how to speak. But its alphabet is way, way simpler than ours.
And when I say simple, I mean really simple. A computer at its very core can only understand two things: on and off. That's it. It's basically a light switch. Every single photo, every game, every line of code boils down to this incredibly basic two-state idea. And this single piece of information, this on or off state, has a name, a bit. We represent off with a 0 and on with a 1. You should think of it like a digital atom. It is the absolute smallest building block of everything on your computer. It's so different from how we think, right? We humans use a decimal system, base 10. We grew up with 10 digits, 0 through 9, and it just makes sense to us. But computers? They live and breathe in a binary, base 2 world. Just those two little symbols, a 0 and a 1, are enough to build everything they do.
Okay, so how do you get from a single 0 or 1 to, say, an email? You group them up. Put 8 of those bits together, and you've got what's called a byte. That's enough information to represent just one character, like the letter A. Then you start grouping the bytes. Thousands of them make a kilobyte, millions a megabyte, billions a gigabyte, and all of a sudden, you've got enough space for your movies, games, the whole shebang.
All right, so we've got the language down, bits and bytes. But where does all this digital stuff actually live? It needs a physical home, a place where these zeros and ones can do their work. And that's where the hardware comes in. That physical home is the system unit. You know, the big box on or under your desk. It's basically the house where all the really important parts that make the magic happen live. And inside that house, the most important piece of real estate is the motherboard. I love this analogy. Think of it as the city grid. It's this giant circuit board that connects everything. The brain, the memory, your graphics card, they all plug into the motherboard so they can talk to each other. So if the motherboard is the city grid, how does all the traffic get around? Well, it moves on what are called buses. These are basically the data superhighways, tiny electronic pathways etched right onto the board that let information just zip between all the components at incredible speeds. Okay, so we've got our city and we've got its highways. Now it's time to meet the one in charge, the component that does all the actual thinking. Let's talk about the brain of the operation.
This is the Central Processing Unit, or CPU for short. It really is the brain of the computer. This is the processor that takes all the instructions, does all the math, and basically makes everything happen. It is the engine that drives the whole show.
And here's a cool thing. Modern CPUs are like having multiple brains. When you hear about a dual-core or quad-core processor, that literally means it has 2 or 4 separate processing units, cores, working together. That's why you can have a video playing, a game running, and a dozen browser tabs open all at once. Each core is tackling different jobs.
Now, you've probably seen a spec like this when looking at computers, 3.4 gigahertz, or GHz. It sounds kind of techy and abstract, right? But what it actually means is, well, it's pretty mind-blowing.
What that number means is that the CPU's internal clock is ticking 3.4 billion times per second. Let that sink in for a moment. Billions of operations happening in the time it takes you to blink. That is the insane speed of modern computing.
And to be even faster, the CPU has a secret weapon, a tiny bit of super-duper fast memory built right into it called cache. Think of it this way. If your main memory is a filing cabinet across the room, the cache is like a sticky note right on your monitor. The CPU keeps its most used info on that sticky note so it can grab it instantly.
But obviously, the CPU can't keep everything on a sticky note. It needs a bigger workspace. And it needs a place for long-term storage. So let's talk about the different kinds of memory a computer uses for every piece of data. You can really break it down into 2 main types. First is volatile memory, and the best example is RAM. Think of RAM as your desk. It's where you put everything you're currently working on. It's fast, but when you turn off the power, the desk gets cleared. It's temporary. Then you have non-volatile memory, like your hard drive. That's the filing cabinet. You put your files in there, and they stay there, safe and sound, even when the power's off. So this all creates a kind of hierarchy of memory based on speed. At the very top, the absolute fastest are registers. They're literally inside the CPU. That's like data you're holding in your hands. Just below that is the cache we just talked about. That's the stuff on your desk. And then you have your main RAM, which is like your entire workbench. The closer the data is to the brain, the faster it can be accessed.
All right, let's recap. We've got the language of bits and bytes, we've got the motherboard city, we've got the CPU brain, and we've got all the different memory types. So now for the grand finale. Let's put it all together and see how a computer actually processes a single instruction.
The whole system is kept in time by a system clock. And no, it's not for telling you it's lunchtime. Think of it as the computer's drummer or its metronome. It sends out a constant, steady electrical pulse, a tick, that keeps every single operation across the entire machine perfectly synchronized.
And with every single one of those billions of ticks per second, the CPU performs this little four-step dance. It's the same dance every time, and it's called the machine cycle. This is the absolute core of what a computer does. So here's how it goes. Step 1, fetch. The CPU reaches out to RAM and grabs the next instruction. Step 2, decode. It looks at that instruction and figures out what it's being told to do. Step 3, execute. The CPU actually performs the task. It does the math, it runs the logic, and finally, step 4, store. It takes the result and stores it back in memory. Fetch, decode, execute, store. Over and over, billions of times a second. That's the magic.
So when you really boil it all down, we went from a simple on-off switch to grouping them into bytes to building this incredible city of hardware with a brain that performs that four-step cycle billions of times every second. That is how a computer thinks. It's a mind-bogglingly fast symphony of very, very simple steps. And knowing that, it just makes you wonder, doesn't it? With all of that power, what are we going to build with it next?